So hello everyone. Uh, Welcome to today's Quantum Spacetime seminar. We are very happy to have Shiroman Prakash from the Albach Educational Institute, and he would be telling us about Bifundamental multi-scalar fixed points. Over to you, Shiroman.
Okay, great. So thanks a lot for inviting me. I'm sorry. I wish I could come in person because that's the main fun of giving a seminar, but we'll have to do it online. So the talk here is a bifundamental multi-scalar fixed points. And most of the work is with the student S Kapoor, who's I think also connected, and he's a master's student at UBC, but he was stuck in Agra because that's his hometown during the first year of COVID. So he approached me for a project, and I think he's undergrad from ITK. Okay, so I'll just begin with some general motivation, which you've probably heard before from me. But anyway, so there's this notion of ABJ triality. So the n equals 6 supersymmetric UN cross Chern-Simons theory with matter in the bifundamental representation known as ABJ theory has an important role, plays an important role in ADS-CFT because when n is large, but m is much less than n, the theory is a large n vector model. And therefore, it's dual to a higher spin gauge theory, except that the higher spin gauge fields are addressed with Chan pattern factors transforming under the group. When n equals m, the theory becomes ABJM theory, and then the large n limit is dual to type 2A string theory on ADS4 cross CP3, or type 2A supergravity if you go to the strong swift coupling limit. So as observed by Chang, Minwala, Sharma, and Yin, in the language of the higher spin gauge theory, the parameter m over n plays the role of a gravitational Tuft coupling, because 1 over n is like the gravitational coupling, and m makes it a Tuft coupling. So when m over n is small, the theory contains an infinite number of higher spin gauge fields corresponding to conserved higher spin currents, and as m over n increases, the tower of higher spin gauge fields somehow coalesce to form strings as the higher spin currents acquire large anomalous dimensions. Okay, so the m over n, and from the field theory side, m over n is similar to 1 over n expansion, but it's not quite the same because when m over n is small, you have only the small summable subset of planar diagrams which contribute in a vector model large n limit. And then as we increase m over n, more and more diagrams are included, but only planar diagrams. And when m over n is finite, all planar diagrams contribute, but they may be weighted by factors of m over n unless m over n is 1. And unlike 1 over n, the parameter m over n interpolates between two large n saddle points. So generically, if you get a power series in m over n, it might have a finite radius of convergence, as opposed to the 1 over n expansion, or at least better behaved. So we can ask the question: Does similar phenomena occur with other examples of conformal field theories with?
Sorry, Shiroman. You must go on, but you mentioned some triality in ABJ. Now, I'm sorry, I don't remember that. Can you briefly mention what's the triality?
So one is the field theory. One is like a higher spin gauge theory, and the other is the string theory.
I see. And now the highest, sorry, just to get sure, higher spin gauge theory is living in the bulk or what?
Yeah, it's living in the bulk. So, I mean, you could call it a duality if you want to, actually. I mean, but they call it, I'm not sure why, that's the reason you called it a triality, because higher spin gauge fields, but basically, so it's in the bulk. When m over n is small, you have these massless higher spin gauge fields. When m over n is large, somehow they coalesce to form strings.
Got it.
That's and it's I mean, in the case of this theory, it's a n equals 6 supersymmetry, and you sort of know the. I mean, you have a string construction, so this is how you get higher spin gauge theory in string theory. So that's why it's interesting. In some of the other cases, we consider we don't have a stringy construction.
And just very quickly, I know you have to go on. From the point of view of the supergravity or closed string theory, if you start with ABJM, which is whatever, either M theory or a type 2A, as you said, on CP, whatever, what do you have to do? Do you have to turn on fluxes to get M?
I think you turn on a B field flux through the CP3.
Okay, through the CP3.
That's right. Shah's right. It's a B field flux through this.
Yes, it's good.
B field flux. I mean, I see in terms of forms, it's a 3-form flux, or what is it? Okay. Anyway, in case you know.
It's like a Wilson loop of B on the 2-cycle of CP.
I see. But there must be some field strength associated with it, or?
Not at the leading order.
Oh.
But then it gets sort of corrected, because then the fields pick up funny periodicities. So, the gravity description is basically identical between ABJ and ABJM. It's only when you look at string theory that they change.
Oh, I see.
So it's actually a subtle, I mean, it's, and from the field theory, you see it's a vector model. From the string theory side, I don't know if it's even that easy to see it.
Oh, I see. Okay, so this is interesting. I should have known this, but okay, thank you.
But from field theory, it's clear it's a vector model because just M is much less than N, so it's you can do everything basically for vector.
I see.
From the bulk, I think some more work is needed to understand that.
I see. Okay, thank you.
So anyway, so the question which people have asked is, does a similar phenomena occur with theories with less supersymmetry? So of course, I mean UN Chern-Simons theory coupled to fundamental fermions or bosons is a line of conformal fixed points dual to a one parameter family of parity violating higher spin gauge theories that doesn't have any supersymmetry. So you can also generalize that to UN cross UM theory and ask what happens as you increase M over N. So hypothetically, those higher spin gauge fields could also coalesce to form strings, and maybe you get a simple non-supersymmetric theory of Einstein gravity in ABS form. Okay, which is sort of an obvious extension. But of course, there are many reasons to doubt the existence of these of stable non-supersymmetric ABS vacua. But regardless of those statements, the question is I mean, we does or does not a strongly interacting non-supersymmetric conformal field theory whose large N limit consists of a web of planar diagrams exist. And so is there some way we can say anything about the strongly interacting limit of this theory that I talked about, these non-supersymmetric Chern-Simons theories, or any non-supersymmetric conformal field theory whose large N limit could consist of a web of planar diagrams, and maybe you could think of it as an indirect test of these nice conjecture, or just a general question you could ask.
Sorry, Shiroman, I did not understand. So does it imply that the Chern-Simons matter theory, that is non-supersymmetric, right? So it will not have any dual or anything?
It has a higher spin gauge dual, that's fine.
Yes.
The question is if you make it a bifundamental Chern-Simons gauge theory. So add another Chern-Simons field. And now make your matter transform in a bifundamental representation.
I see.
Then if you increase M over N and also increase the Tooth coupling, do you find that the enormous dimension of higher spin currents diverges when m over n is 1 and lambda is taken to strong coupling, which depending on the shift n over k, I mean, it would be, and people would say that probably shouldn't happen, although I'm not sure a reason from the field theory side why it shouldn't happen. So
yeah, actually, if I can just sort of pick up on that. I mean, again, I know you have to go further, but which is what exactly is the precise, I mean, sorry, but the weak gravity conjecture in the context of the theory, say, that Sachin was mentioning, the theories you've studied, say you start with just SUN with fundamental matter, it's clear that theory exists, etc. Okay, but it doesn't have a smooth gravity dual, I agree. Now you introduce a UM and M is order unity, N goes to infinity, presumably those theories exist. And you start cranking up the ratio M over N. What exactly is the precise statement that an instability must occur for M over N of order 1? Is that, would that
well, okay, these guys probably aren't aware of this conjecture. I mean, Oguri and Bafa, I mean, they've not cited it and all. So I don't know what's the precise statement. I mean, my guess for assuming this conjecture is correct is that the precise statement would be, of course, you can make m over n equal to 1 and keep lambda 0, because then that's just a free theory with now you increase lambda, and maybe what happens is, okay, you have two regulators. You have the Tufts, you have the Yang-Mills regulator for k, and you have the dimensional regulator for k, and they're related by a shift. If it's supersymmetric, there is no shift, right? Because the fermions and bosonic shifts cancel. But so maybe you can reach because the shift, you can't reach strong coupling in some sense. But yeah, I mean I don't have anything concrete that what would go wrong in this theory. I'm going to construct some other theories where you see something, the instability emerge.
I see. Okay. Just sorry, but just Shiraz, do you have any comments on this? I mean,
it's very. I find it very confusing. But let me just say what I think. I think what they would say is that the prediction is that this cannot reach gravity. That you take m over n to be 1 and lambda to be as large as you can, and you get some theory, but it will not be gravity. It'll be some complicated string theory for which they don't have a conjecture. I think this is what they'd say. I find this thing also confusing, because you see the arguments that they use for the weak gravity conjecture seem very general and don't seem to depend on being precisely at the gravity point. And in fact, much of the original evidence for the weak gravity conjecture came from stringy corrections to gravity. Extremal black holes went in one way rather than the other, using stringy corrections. So I find it confusing that they will admit stringy sort of ADSs, but say that as long as it doesn't continuously connect to gravity, it's okay. But I think this is what they would say. This is my feeling.
I see. Yeah. Okay. Thanks. Yeah. Go ahead. Sorry, Shiroman.
No, I mean, I've never. I guess the question, you can't reach strong coupling, so the anomalous dimensions maybe never diverge. They just.
But since they seem to at least say they have a sharp conjecture one can test, then it should be formulatable in some sharp.
I think it would be nice to formulate it in this theory. But what I'm going to do is because it's hard to really say anything concrete about these theories in this limit. Like if you use bootstrap, the problem with Chern-Simons theories is that the fundamental fields are not gauge invariant. So usually, so it's a little bit more technical to do bootstrap. These would probably, someone can try it. But I thought maybe we'll try simpler examples of theories. So the simplest example I think one can think of is
Shiroman. A question. Sorry, a basic question. Is there a particular reason why the choice of K for both groups was correlated, K and minus K?
If M equals N, then this is parity invariant.
Yeah, but now that you have broken it.
Yeah. So I mean, I've studied, if you just do start perturbative studies, you can put them different. And especially without supersymmetry. With supersymmetry, I think you need them equal for n equals 6, but here you might as well keep them different, and that's the most general.
Thank you.
That's true. Look, I mean, it's conformal when they're different as well. So.
Sorry?
Yeah, I mean, you still get a conformal field theory.
Yeah. Okay.
And if you wish, okay, I mean, if you make a perturbation as, because it's a marginal deformation, that's sort of dual to an axion, going from K1 and K2 being equal to them being unequal. It's like a parity violating scalar in the bulk. So you have like a dilaton and axion in the dual, in the two domains.
So are there more corners now in the theory space where the dual description can be found out? Given that there is this additional parameter, like quadrality or something, whatever.
Yeah, I haven't thought of any theory, any accessible corner, but
okay,
I can't say that there isn't one. Maybe with very unequal K, you can do something. So,
okay.
But yeah. So this theory in general in the Tuff limit, you have actually, it will be dual to like axion, dilaton, Einstein Maxwell gravity in the optimistic case, because you can change the levels unequally.
Yeah, I'm sorry, along the same lines, at the gravity point, so if we are at the ABJM point, if we change M and N, you make M not equal to N, then as you said, it's this B field flux of the CP2, or this Wilson line of B field of the CP3. Oh, do you know what the analog of changing K is? K not equal?
Well, in that case, I'm not sure it would be supersymmetric, but it should be some sort of axion. Is what else can it be, right?
Right. So there should be a new supergravity solution one should be able to find, which will not preserve n equals supersymmetry, but one should be able to find it in perturbation theory around.
Right. That has some sort of axion turned on.
And nobody's done this, right?
Well, these are some of the papers that do stuff with this, but I don't think they've done this particular thing. Yeah.
Okay, thank you.
I mean, that you could do just even for UN cross UN, right? With different Ks and ask what's the supergravity.
Yeah.
Right? Yeah. I mean, it sounds very much like it'll be some, okay, anyway. Yeah, it'll be some axion. Yeah. Okay.
I was wondering whether a level rank duality could play a role.
There's an ABJ duality between different theories as well. That's sort of like Givion-Kutuzov duality.
Okay.
Yeah. So anyway, so what I thought was, okay, if you're interested in this question, we can look at just a much simpler context, which is just scalar models without engaged fields. So maybe the first thing you can try is, can you generalize the critical ON vector model in 3 dimensions to critical ON cross OM model, and study that in this limit where M and N are both large and alpha set fixed. And this is dual to this is the first conjectured theory dual to higher spin gauge theory. So there's this symmetry M goes to N. And okay, so this seems a natural question to ask. And what is a side remark is that there's a symmetry M over N, so that implies a sort of S duality in gravitational coupling. So it turns out in the context of phase transitions when cross OM, fixed points of multi-scalar 5-4 theory have been studied extensively, that they're sort of like frustrated anti-ferromagnets using mainly the epsilon expansion, but very recently this paper, Henriksen with Sturdio and someone else have studied it using Bootstrap, but they mainly consider M to be 2 because that's what's relevant for experiments.
Sorry, Shiroman, so you've got no Chern-Simons here, what you're saying.
Yeah, so now I'm just forgetting about Chern-Simons.
I see. And can you say again what the Z2 is, please? You maybe said.
Okay, so if you have, so here you know this field will be like 10, it will be like phi AB, where A is in ON, and let me try to write. So it'd be, can you see this or?
Yeah.
Yeah, so phi AB.
Oh, no, sorry. See the,
No, sorry. Well, I don't need to write it. Let me just. Okay. Well, the point is that there's two. It's like if you have a vector of ON times a vector of OM, and you multiply both by a minus sign, that does nothing. So -1 times -1 is in ON, the Cartesian product of ON times OM, but it's not in the. It doesn't act on your fields.
And the Z2 is regarded as gauge?
No, the Z2 is just your global symmetry is ON cross OM mod Z.
But by saying that it's mod, oh, I see. The global symmetry is, I see.
Yeah, the Z2, whether it's part of ON and OM are same, I think.
Yeah, it's just that you have a vector of ON times a vector of OM. So you can only multiply them, like if you multiply both by a minus sign, it does not.
I understand.
So you might as well say ON times SOM or something like that, right?
Yeah, I guess some reason people say this, so I just use the word.
It's not very important what you're saying.
It's really not important. I often just write it ON cross OM.
Sorry. I thought you were
the only thing, I mean, sometimes when people write ON cross OM, they mean a theory where you have one field with OM and another field in the OM, which is like a biconical model. So if you write mod Z2, it means bifundamental. That's, yeah. And yeah, so it's been studied in the literature, though most people aren't interested in the limit where, I mean, I've not seen anyone interested in the limit where M and N are both large, but you can extract results from it and from the literature, and at least to a few orders in epsilon, it finds that it turns out that there is a sort of a bifundamental fixed point, but it becomes that there are two fixed points and they merge at some critical value of alpha, which you can calculate in the epsilon expansion, and it's 0.1 plus 0.1 times epsilon plus 0.078 times epsilon squared. And maybe higher orders are known, but below this value, above this value of M over N, you find that it's a complex CFT. So there's some scaling dimensions of operators become complex.
Sorry, Shiroman. Yeah. I mean, I can't do it in my head. So 5 minus 2 root 6 is bigger or plus what?
Yeah. So in the second line, I put the numbers.
Okay, so
this is the same
thing. Okay, I see. So as long as M over N is less than whatever that number is for small epsilon, then you get a fixed point.
Then you get a real fixed point. Otherwise, it sort of becomes complex. It's like you have a beta function which crosses the x-axis, and let me just draw it. So you have now I guess you can see. So it's just like, okay, there's a beta function, and at some value maybe I should draw it upside down. So it would be like this, and then as you change alpha, there's no longer a fixed point, you get a complex. Okay, the value of alpha critical in D equals 3 is unknown. So earlier I had just known these numbers. When making this talk, I plugged in the numerical values, and at least these three seem to be positive. So hypothetically, in D equals 3, it could be closer to 1, but it's unlikely.
So the beta function is like for trace of phi transpose, phi transpose?
Yeah, so we have two coupling constants. We have like a phi transpose phi transpose phi trace. Okay, that we can call the single trace coupling constant. Plus you have trace of phi transpose phi squared times G2. And you define appropriate TUF couplings for these two guys. And it's a coupled set of beta functions, and below this, I mean above this value of alpha critical, G2 becomes complex. Is that answering your question?
Yes, completely. Thank you.
Yeah, and the beta functions depend on alpha, so it's just a parameter in the beta functions, and even the first non-trivial beta function, you can see it. So
Shiroman?
Yeah.
This is also a system, very similar to the system that Komar-Godsky and friends study in context of symmetry breaking and such, right?
Yeah, I don't know. Can you remind me what that system?
I remember that they had this bifundamental type model. Very similar to what you have. I forget what the differences were, and the analysis was also of basically beta functions. But maybe I'm missing, some key distinctions. But I don't know. Shiraz, do you remember Komar-Godsky's talk?
I can't remember well enough. Sorry.
Okay.
Yeah, I think I didn't.
Okay. No, I just in case you had looked at those and found any similarities.
But I look at it. I didn't see. I mean, I tried to look at like everyone that has studied this particular theory.
Okay.
At least up to 2018, these guys cite everything. And maybe I missed that. But okay, this is a theory, and alpha critical is unknown in D equals 3, of course, but it's probably less than 1. You could try to calculate it using numerical bootstrap, and there is numerical bootstrap using the M equals 2 theory. So maybe generalizing that to larger M is not impossible. I mean, okay. So you can study the fixed point for all values of alpha, just that it's a complex. Some enormous dimensions become complex, and of course, if you calculate the enormous dimension of the scalar field phi, it has a maximum at alpha equals 1. So just confirm the expectation that alpha equals 1 is strong coupling. So basically we conclude that the fixed point becomes complex before strong coupling is attained, which is sort of in accordance with this conjecture.
Sorry, can I just check? Did you so there was a symmetry among interchange of M and N that you mentioned?
Yeah. So
why doesn't that?
If M over N if is also bigger than 1 over alpha critical, it's also real. Okay.
Sorry, I didn't understand. M over N seems special here, as opposed to the.
Yeah. So I wrote this assuming M is less than N. If you want, so if M, you can also say when M over N is bigger than 1 over alpha critical, it's also real. The fixed point also exists.
Okay. Thank you.
So it's, I mean, when you write down the full expression, I find M and N it's symmetric. In M interchanges N. But yeah, so here that's what I was saying in this line.
I see.
But it's sometimes convenient just assume M is less than. Right. So here we find that the theory is complex, and generally if you have a complex scaling dimension, it translates to a field with a mass below the PF bound in terms of using the ADS-CFT dictionary. So hypothetically, you could have a formal holographic dual for this fixed point, and maybe it contains a small number of massless fields, but it presumably also contains at least a few fields with masses below the PF bound. And that's, I guess, in accordance with what you expect from weak gravity. Though there are, there's more to be studied, like get alpha critical exactly in equal state.
If you look in the epsilon expansion and you work out the anomalous dimensions of several of the operators, when the coupling constant goes complex, do many of them gain complex dimensions or only a few? Or do any of
I've only looked at gamma phi, the mass dimension, and maybe the quartic anomalous dimensions. Not even the high spin ones. The quartic ones become complex because I guess one of the coupling constants is complex.
Right.
The mass one, I don't think it becomes complex. I'm not sure.
Right. So the conjecture that there's some field that maybe one or two fields that go below the BF bound, but all the rest are okay, would sort of be the statement that most of the anomalous dimensions look okay, right? Yeah.
So this a few is not necessarily a few. There would exist fields with masses below the BF bound. How many? I didn't.
Yeah. But
I didn't estimate it. You could try to estimate how many with a calculation.
Possibility that when the coupling constant goes complex, all of them pick up a complex one.
Well, at least to the first order, this guy didn't get a complex part. So that means like the limit of the higher spin gauge fields as S goes to infinity would be like twice this. So I expect that the higher spin gauge fields for S larger than some value would probably not become complex.
Okay, thank you.
But so it's more this like smaller spin fields where, like in SYK, when people do it in higher dimensions, it's the fields with smaller values of n and smaller values of s that sort of become complex first. I mean, it's not the large spin, large n fields don't become complex. So I mean, but this is guesswork. But yeah, so I mean.
Yeah, I was just wondering that if the scaling dimensions were some function of the coupling constant, and then the coupling constant becomes complex.
Okay. The point is the single trace coupling doesn't become complex. It's the vector. It's a double trace coupling that becomes complex. So to leading order in a lot of the things just don't depend on that.
Okay, thank you.
Yeah. So what we did here was we thought we'll just generalize this to, we'll look at other dimensions. We'll look at 6 minus epsilon and 3 minus epsilon, though here I'll only talk about 3 minus epsilon. Maybe 6 minus epsilon is actually more analogous to the other case. So the case of 3 minus epsilon is a little different because as I'll explain to you, I mean, because basically when m is 1, you actually don't have a theory necessarily dual to a higher spin gauge theory, as we'll see. But you can try to you can just study the same physics in the other cases of 3 and 6 minus epsilon. It's a natural question, and so here we're going to study a sextic model in 3 minus epsilon dimensions with ON cross OM symmetry. Okay, and what are the interactions? So there are, it's sextic, so you have a single trace interaction, which I represent here. So the red lines are OM index contractions and blue lines are ON. You have a double trace operator and you have a triple trace operator. And so these would be the 3 sextic operators in a bifundamental theory in 3 minus epsilon. And you also have quartic operators. So there's a single trace quartic operator and a double trace quartic operator, like I mentioned earlier. These are both relevant now, and in 3 minus epsilon, and you have the only quadratic operator is the mass term. So at any fixed point, you have to tune both the quartic couplings and the mass term, in addition to any sextic couplings. So usually the sextic model with you have ON is considered to be tricritical because you have to tune one quartic and one mass term.
Mm-hmm.
This theory is at least one parameter more critical because you have two quartic couplings. So that's probably why it's not studied so much in statistical mechanical literature. In 4 minus epsilon, going to OM doesn't actually add any more relevant couplings. So, but in this case now we have a theory which is more, at least one parameter more critical, and will usually the sextic operators at least one is relevant. So.
But this is different from what you talked about previously, right? There it was quartic model in 4 minus epsilon.
Yeah, so that was a quartic model, and
okay.
Now I'm going to talk about the sextic model.
Okay,
and mostly that's what we'll talk about here, is the sextic model. So the sextic model now has 3 coupling constants instead of 2, 3 marginal coupling constants, classically marginal, and 3 relevant couplings which we tune to 0. Okay, and we want to see the fixed points of this theory, and we'll look at the fixed points. There are actually 2 limits we can look at them at. One is the main limit, which I was discussing, which is the limit m over n is held fixed and m over n are both large. But you can also study this in the vector model large n limit, where n is large and m is held finite. This is just because you can solve it in this case, I guess. Yeah, both these cases you can sort of get exact. Well, in this case you can get exact fixed point. It's a vector model, so you can solve it. So we solve it, and I'll tell you the results. So.
Sorry, and Shiroman, you're turning the quartic coupling to 0, right?
Yes.
Okay, so this is like the regular boson theory rather than the.
This is the regular boson theory. When you turn on the quartic coupling, then the sextic coupling usually becomes irrelevant, at least for the ON vector model.
Yes. Okay, thank you.
Sorry, Shiroman, I'm very sorry, but
yeah.
I realized there's something basic I didn't understand about the earlier quartic model you described. Yeah. Can I just slow you down? So let's not go all the way up to strong coupling, but we stay within that limit alpha less than whatever you had found, m over 0.1. Now you have nice critical points in the epsilon expansion, and there were no unstable directions. That is, all anomalous dimensions were real. Is that correct?
That's correct.
I see. Okay, so it's I mean, if there had been a gravity dual, of course it wouldn't be smooth and so on, then everything would have been above, below, whatever, within the BF bound.
Yeah, it's just that you have higher spin gauge fields which probably have masses, but they're not infinitely massive. So it's somewhat reminiscent of SYK.
I see. Okay, that's itself interesting, isn't it?
Yeah, and I mean, it's pretty clear that these exist for alpha less than some value. I mean, so it's order 1, and it's a theory you can hope to study via numerical bootstrap. It's definitely. And I don't know, you alluded to this higher dimensional SYKs. Will you be getting to that? I don't think I'll
okay.
I can just quickly tell you about that right now if you want. If that's...
Oh, no, don't derail your talk. But at some point, I mean, what I wanted to come around to asking you and everyone else, but maybe it's easy to wait, is then whether these higher spin fields with some amount of mass are the natural higher dimensional generalizations of SYK, as you were saying. And that's not exactly what Mukund and all looked at, as far as I know, but maybe...
No, what Mukund looked at is different. But their models also sort of, when m over n is small, they reduce to the critical.
Come to it later.
Actually, I may not be able to.
Okay.
Come to it, but we'll see. Yeah. We can definitely discuss that if not online, off.
Okay.
Offline.
Thank you.
but yeah, in those theories, you find that the spectrum, you can calculate alpha exactly, and like, you know, in d equals 3, they get a value of critical value of alpha, and you can also do it in other dimensions, like in d equals 5, and you get a smaller critical value of alpha.
Okay.
So it seems like, at least for scalars, this phenomenon is sort of generic, that as you increase alpha beyond some value, whether it's this model or the SYK type model, you get complex dimensions.
Just to be clear, I mean, just to understand, so you're thinking of this as the first step in constructing a larger class of models which could have Chern-Simons couplings for the OM and ON, right?
Yeah, I mean, of course, if alpha, you know, so it could be you add a Chern-Simons field, this value of alpha will also change. I mean, the computation would change.
Right, but you want to do some gauging to get a string dual. So
yeah, you do want to have gauging the strings, but in SYK they don't necessarily gauge. Yeah. Right. So you know.
Right, but one way of thinking of that is here, if we can think of this as gauged, but with both k's going to infinity, then it's more or less your model, right?
Yeah. So here you have that option in d equals 3, but the challenge with gauge is that it makes bootstrap harder. So because you don't have, whereas here you can the motivation is here. Okay, we're doing epsilon calculations, but then you can really answer these questions if you decide they're important. You can try numerical techniques to answer them.
It's a very simple cut of theories, but it's naturally situated within a larger class of theories, right?
Yeah, it's naturally situated with the class of gauge theories. Although in 3 minus epsilon, we one of the theories we approach will be 2-dimensional. So I don't know if you can just gauge it as
Thank
easily. You. Yeah. Okay, so this theory has three sextic operators, and we're just going to study the beta functions for these operators. So there's the following TÜV couplings. If you define them, it takes care of both large and limit. So if M is finite, this is the usual TÜV couplings for a vector model. I mean, all the 3 interactions are effectively triple trace, and if M is large, it gives you the scaling for the bifundamental limit that we apply. Okay, and these scalings don't preserve the symmetry between M and N, but that is, if alpha is order 1, that's just a matter of notation, because you can just redefine the couplings by multiplying by alpha. And when alpha is less than 1, they do define possibly different larger limits, but that's a minor one. Okay, so here, so this is what the beta function looks like to 2 loops. And it turns out in this case you find a unique non-trivial fixed point for any finite value of alpha. Okay, which is here. So unlike the case of the 4 minus epsilon, where there's only a fixed point for some range, at least if alpha is finite, there is a fixed point for any value of alpha, which is a difference. And we also computed for loop and 1/n corrections. If you include for loop corrections and compute the anomalous dimensions, then this is the anomalous dimension of the fundamental field of the field phi, which turns out to be independent of alpha. And the mass anomalous dimension is also independent of alpha. It's 32 epsilon over 27. The quartic anomalous dimensions for the quartic operators, they do depend on, well, one of them depends on alpha at the second order. That's the single trace quartic operator. And we can also look at stability, and the stability matrix has these eigenvalues, which is, well, these, when epsilon is small, it's stable in 2 directions and unstable in 1. Okay, and these scaling dimensions and stability matrix obey all the relations you expect in the large N limit.
Sorry, what is the stability matrix?
Stability matrix is d beta, d lambda at the fixed points.
Mm-hmm. So what does this mean for conformal field theory?
It means, is it an attractive fixed point in the IR or a repulsive fixed point?
But
so it tells you is the sextic coupling
that one of these operators.
What?
So in conformal field theory, this means that one of these operators is a relevant operator.
Yes. One of the sextic operators is relevant. The other two are relevant. I mean, it's yeah.
So it becomes even more critical, right?
Even more critical. Yeah.
Even more. Okay. Fine.
But sorry, Shiroman, just I might be losing the thread. So for this model, unlike the earlier one, for any value of alpha, first of all, at least in the epsilon expansion, you get a fixed point. And moreover, all the anomalous dimensions are real, etc. What is the story?
Yes. So for any finite value of alpha, when epsilon is sufficiently small, you get a real fixed point, and the anomalous dimensions are all real.
I see. So what would you be bold enough to say that if alpha becomes, first of all, there wasn't a alpha going to 1 over alpha type of symmetry, or maybe I missed it?
There is a symmetry. So when if you thought this, okay, you find this is symmetric and alpha goes to 1 over alpha.
Oh, okay.
So everything has this symmetry, alpha goes to 1 over alpha.
It does. Okay. And then if alpha goes as far as 1 or its maximum value subject to that symmetry, would you say that you are in the analog of the gravity limit? Or I mean,
okay, so at this point it looks like that way. What I'm going to point out is there's a subtlety when alpha is small. Actually, not when alpha is large, but when alpha is small, there's this subtlety, and so that sort of it makes it an open question. But from so far, like this calculation seems to suggest that you could have a theory it works for alpha is 1. Mm-hmm. So maybe if it survives when epsilon goes to 1, it's a gravity dual, right? I mean, and that's interesting. Mm-hmm. Mm-hmm. Now we'll look a little more carefully and find there's some reasons to be skeptical of that. So, but as of now, that's the conclusion at this slide. Yeah.
Okay. Let me ask it. You're working in 3 minus epsilon.
Yes.
So why are you interested in alpha going to 1? You're interested in a 2-dimensional theory.
Well, epsilon goes to 1. Yeah. Well, just by analogy from 4 minus epsilon to 3, here you could try to study a 2-dimensional theory in the epsilon expansion. Right. Okay. We'll also I'll come to a 3-dimensional theory in a moment. Okay, but if you're just going to proceed by analogy to the phi cube 4 theory in 4 minus epsilon, the question is, can you define a 2-dimensional theory?
Okay. All these theories in 3 dimensions become free, right?
This theory in 3 dimensions becomes free.
Yes.
There's just one fixed point, and
right. Yes. And that's just a free fixed point in 3 dimensions, but it becomes an interesting fixed point in 2 dimensions. Hopefully, that's the point.
Hopefully, and we'll ask now. We'll try to ask, does it survive 2 dimensions?
Yeah.
Okay.
So Shiroman, here this is just an epsilon expansion, right? M and N could be just finite numbers.
Yeah, M and N could be just fine, because I don't have any way of studying the theory at finite alpha.
But then why the singularity at alpha equal to 0 is a bit puzzling, because I would imagine you can do a separate calculation at alpha equals 0.
So the singularity at alpha equals 0 is consistent with the ON results. I'll explain that.
Okay. But because this is divergent at alpha.
Yeah. So that is the case, and in fact, we'll discuss that in the next slides.
Okay.
Yeah. So, but here are the plots of the anomalous dimensions of the operators, the quartic operator and sextic operator, which as a function of alpha. So they're symmetric, and alpha goes to 1 over alpha. So I didn't need to go beyond 1. And they both have their maximum at alpha equals 1. So they're both which is what you expect, so that alpha equals 1 is strong coupling.
Mm-hmm.
Okay, but as you see near alpha, when alpha becomes very small, these anomalous dimensions could, become arbitrarily negative. Here I chose epsilon as 0.1. If you choose epsilon, for any value of epsilon finite, if you choose alpha sufficiently small, these guys would go below the unitarity bound. This is actually not surprising because, the tricritical vector model, it turns out it only exists for epsilon less than 36 over pi squared, 36 pi squared over n, which tends to 0 as n goes to infinity. So in fact, for the tricritical vector, the usual ON vector model in 3 minus epsilon, you cannot go beyond a value epsilon, which is suppressed by 1 over n. I
see. What happens if you go beyond? Just the fixed point disappears.
Well, it becomes complex, I guess.
Complex, okay.
Yeah, and I'll explain exactly why in next.
But here n need not be taken to be infinity, right? You could just take n to be 5 or something, and then
yeah. So for finite n, you could do it, but here we're looking at m and n both large.
Oh, I thought it's an epsilon expansion. You don't.
Yeah, it's epsilon expansion. And I'm plugging in m and n both large. Okay. So to see how it depends on alpha in the limit m and n. I mean, we have the beta function for finite m and n as well, but yeah.
Okay. So my question is, this beta function with finite m and n. Do you see any issue at n equal to 0? No, right? It's just an artifact of this large m limit.
No, you find that there's this critical value. So you can take m goes to 1 and keep n large. And then this is what you find that it. Okay.
Yeah, fine. Thank you.
If you take m and n both small, then there's really nothing you can say because epsilon is. Yeah. Okay, so we can try to understand the alpha goes to 0 limit better. Okay, by just keeping terms which are proportional to alpha in the beta function, to first order and alpha. Okay, first order and m over n. So these are the terms in the for loop beta function which are linear in alpha. There are terms which would be, alpha squared that we dropped times lambda 1, and hypothetically there could be higher order terms. Lambda to the power 4 or 5, which are from higher loops. However, the complete beta function of the theory can be expanded as a power series in alpha and lambda. And in fact, you can argue that the for loop beta function given in the previous slide is actually the complete beta function and to all orders in lambda, but only to first order in alpha. Okay, and that's just because the nature of these triple trace couplings and the n counting. And and this is a well-known property of the 1 over n beta function of even the ON model. Okay, and the reason for that is as follows. So these are the sort of diagrams that you would contribute to the beta function. So this is just tree level, and this is a 2-loop diagram and a 4-loop diagram and a 6-loop diagram. So I claim the 6-loop diagram has to be order alpha squared. So the only diagrams which are order alpha will be the 4-loop diagram or less. Okay, and the reason is, but if you want to see the reason, okay, an L loop correction to the interaction vertex is proportional to G to the N, where N equals L over 2 by 1. And that's including the free G. Okay, if you count the number of edges, there are 3 times n minus 1 internal edges or propagators. So the largest power of n for such a diagram is the total number of, it's a simple graph theory. Okay, I'll give you the arguments. It's the total number of disconnected cycles formed by the internal edges. And that has to be the number of internal, the most number of cycles that you can contain is the number of internal edges over 2, the floor of that, because your graph can't contain any tadpoles. So if you count, so the largest power is n to the floor of 3/2 times n minus 1, where little n is the number of vertices. And if you plug back into loops, you find that the maximum contribution for an L loop diagram is lambda to the L by 2 times n to the minus L by 4. So in other words, the top 3 diagrams are order 1 over n, but the bottom diagram is 1 over n squared. And if you include factors of m, the best you can do is you can take a 1 over n squared diagram to make it alpha squared. Okay, so in essence, the for loop beta function is the full beta function to first order in alpha.
So roughly speaking, this is the argument that if you work in the trace fields, the theory is weakly coupled. So there should be only a small number of loops in the trace fields.
Right.
Thank you.
Right. So there are any other corrections are order alpha squared. So just by keeping alpha sufficiently small, you can ignore them, and that means we can use this beta function to do 2 things. We can find fixed points that are valid into all orders in the parameter epsilon tilde, which is epsilon by alpha, because here you just divide by alpha, and this depends on epsilon tilde by alpha. You can also use this beta function to determine interacting fixed points in d equals 3, because any higher loop corrections to the beta function in d equals 3 can be made arbitrarily small by reducing alpha. Okay, so any fixed points you find for this would survive higher order corrections, because those will be suppressed by powers of alpha, so they can make them arbitrarily small, unless the fixed point has a marginal direction, in which case it may or may not survive higher order corrections. And higher loop corrections could lead to new fixed points, but they would be at strong coupling, because you would have to go lambda order alpha to get the new fixed point. Okay, so is this limit is clear? All right, so now we can find zeros of the beta function to all orders in epsilon tilde.
So sorry, Shiroman, just to make sure, even your first point, first of all, going only up to linear order in alpha is because alpha is small. And then furthermore, you would keep epsilon over alpha small, right? If you were doing that expansion.
Epsilon, it turns out all orders in epsilon over alpha.
I see.
Okay, and that's because there are no other terms which are order alpha. Everything else in the beta function, if it's lambda to the power 4 or lambda to the power 5, it'll be times at least alpha squared.
Okay.
So this is the fact that you can solve a vector large n limit in every dimension.
Yeah.
You don't need an expansion for a vector limit.
Yeah, but because these are triple trace couplings, you actually can't go to all dimensions. The parameter you can go to all orders in is epsilon tilde, which is epsilon over alpha. Okay, because in the literal large n limit, the couplings are just marginal. It's a triple trace coupling. So this is like a 1 over n correction.
Right.
So it's a little bit less than what you get in other vector models, because epsilon still has to be small because alpha is small. Okay, so you have a parameter epsilon tilde, like a tuft epsilon, which you can go to all orders in. You can't go to all orders in epsilon.
Is this the fact that you had something sort of marginal only in 3? I can't understand why in the vector limit why we could just solve the problem literally at large n. Of course, we could just solve it in every dimension, and then we could do sort of one loop to get beta functions in every.
Yeah. So literally at large n, you plug in alpha equals 0. And everything is just totally marginal.
Right. Now the beta functions, as you say, are not leading order in large n, they're 1 over n.
Yeah. And now if I look at this beta function, I'm assuming alpha is small. So I divide by alpha and I get this parameter epsilon tilde. I can solve it to all orders in epsilon tilde, but epsilon tilde is epsilon by alpha.
Because you're looking at a fixed point where these two couplings, these two contributions balance each other.
Yeah.
But we could also have had other couplings, other fixed points which existed even in D equals 3. So it didn't need to be balanced by epsilon. And those...
No, you can look at D equals 3, which is epsilon equals 0.
Right.
So, in fact, that's probably what's most interesting. I mean, is just keep epsilon 0 and now let's look at D equals 3.
Right. And then at small alpha, we could then just look for fixed points that are not near 0, right? Not near
lambda equals 0.
Not near lambda equals 0, right?
Yeah. Epsilon is 0 because they're in D equals 3, but they're interacting fixed points.
Right. And is there some reason we couldn't do the same at epsilon equals half? At leading order small alpha?
I mean,
is it just...
the point is here you'll get an alpha.
I see.
Well, if you just look at this diagram, this level, and you remove alpha from the thing, this only depends on epsilon by alpha. So you can clearly take this to be any order. Okay. But if the point is then alpha squared corrections, I think would change the
thank you.
Behavior.
I'm just trying to understand, is the physical point that this thing was only marginal or near to marginal in D equals 3? And
that's also true. I mean,
that's why we need to be at very small alpha to be able to do this kind of perturbative beta function. Very small epsilon, right? To do this kind of beta function.
I think so. Yeah.
Okay, thank you.
Otherwise, if alpha is 0, of course, in other dimensions, it's not that it's marginal, it's just that it's 0. The couplings are literally 0.
Right, okay.
Right, so it's only marginal when epsilon is 0 also. Yeah, if epsilon is non-zero, these couplings are just fixed to be 0. And that's
right. So otherwise, you're comparing some classical kind of push to the beta function with a quantum one, and that's...
Right. Okay,
thank you.
Right, so we only can study it near D equals 3, but that includes literally interacting fixed points in D equals 3.
Okay, got it. Thank you.
Shiroman, maybe I'm confused, but I thought I saw some 1 over alpha term earlier in the beta function.
Let me see. Well, this is...
Yeah.
No, so yeah. If these are the anomalous dimensions.
Oh, anomalous dimensions. Okay.
In the beta function with the choice of two couplings, there's no 1 over alpha.
Fine.
Okay. The anomalous dimensions had a 1 over alpha. Yeah. So this is the full beta function, and of course, it still retains the property of the large n limit in the sense that only the lambda 1, the single trace operator, enters in its beta function, and single trace and double trace are in the double trace beta function. So it's not very hard to solve. And essentially the solutions are determined by the value of the single trace coupling. Because given that you can...
Sorry, Shiroman, I'm very sorry. Just to make sure that first point then was, is it correct to say then was, you'll solve in alpha going to 0 limit with epsilon over alpha held fixed to any value?
Yes.
Okay.
Any value.
I got it. Okay, go ahead, please. Thank you.
Okay, so we do that solution, and basically the main thing is the beta function for lambda 1, because everything else depends on lambda 1, and that's just a single. The beta function for lambda 1 in this limit only depends on lambda 1, so I can just plot it. And so this is the beta function as a function of epsilon, or really it's epsilon by alpha, because I'm keeping epsilon to be proportional to alpha. So when epsilon is 0, you have, of course, the fixed point where everything is free, and you have this one interacting fixed point. So this is a stable fixed point. This other. So can you see my mouse, or is it?
Yes.
It doesn't.
Oh, we can see it.
Okay. Yeah. Well, yeah. So this fixed point here. So it's under an IR flow, it would flow to the free fixed point, and here it would flow back over here. So it's a UV stable fixed point. Then when you turn on epsilon, you now have this interacting fixed point in the which is proportional to epsilon, which is sort of like the fixed point we found earlier. And this is also the UV fixed point. And then at some value of epsilon, which is epsilon equals 9 alpha by 2 over pi squared, they merge.
I see.
Okay, so this is so we find that essentially there are two solutions. One is this infrared solution, which vanishes as epsilon goes to 0, and a UV solution, which doesn't vanish when epsilon goes to 0. And both these solutions merge for a critical value of epsilon.
Just show that diagram once more. I'm sorry, just once. I see. So just say again, so which two are merging in that green top?
Yeah. So if you look at epsilon equals 0, there are only two fixed points. There's the free fixed point here.
That's right.
And
that one. Yeah.
Point here.
Yeah.
Okay. And basically, under this guy will flow to this guy.
Right. I got that. Yes.
Now, if you turn on epsilon, you get the second fixed point, which is proportional to epsilon, and that's the IR fixed point we found earlier, roughly.
Right.
And you have this.
You already have that. Okay, and they come together. I got it.
They come together. You always have this free fixed point, which can flow to the IR fixed point.
Correct.
But once they merge, instead, it'll just flow to infinity.
Got it. Okay, thank you.
Yeah, so the upshot is that at least for small alpha, this fixed point only exists for epsilon critical equals 9 over 2 pi squared times alpha. So at least for small alpha, the bifundamental fixed point does not extend to the equals 2, and there's also this completely analogous calculation works for the vector model. Okay, but you could imagine calculating higher order corrections to this. And so there's basically epsilon critical of alpha is some unknown function of alpha, which we determine to first order. If we computed higher order corrections, the merger location would change by some order epsilon alpha squared term. And that in practice, that would be an 8-loop calculation. So we could use this result to epsilon to estimate the range of epsilon for which the fixed point is real, which maybe you shouldn't do because it's just first order in alpha, but that would give you epsilon critical is 0.45. So even you can also try to use a two-sided Padé approximation because this is symmetric and alpha goes to 1 over alpha. So okay, and that would give you something which is like this. So here's the plot of epsilon critical. So we know epsilon critical as when alpha is small, which is this dashed line here. We also know epsilon critical when 1 over alpha is small, which is this other dashed line. And in between, it's some unknown function, which the more orders you calculate, the better you can estimate it. This is just a schematic guess. But looking at this graph, you might say it's unlikely that epsilon critical is actually 1. I mean, when alpha is 1. So this is alpha is 1. Though I guess you can't say anything without higher order calculations. But this is the conclusion.
Shiroman, you have in the small epsilon region, you have that fixed point far away, this Pisarski fixed point. That fixed point, should I think of that as being more strongly coupled than the intermediate fixed point as we change epsilon?
Yeah, it's a strong. It's more strongly coupled. I mean, I did calculate the anomalous dimensions, but I didn't put them here. But yeah, it's more strongly coupled because when epsilon is 0, this has a non-trivial coupling constant. So at least for small epsilon, it's more strongly coupled. So.
And as you change epsilon, it becomes sort of weaker and weaker in coupling. Should I think of it that way?
Yeah, it becomes weaker in coupling, while the infrared fixed point becomes stronger.
Right. So in a way, the guy that is perhaps the best candidate for something very strongly coupled is that other guy at epsilon equals 0. I mean, if that
Alpha equals 1. Right. ND equals 3.
ND equals 3, and then maybe a bifundamental version of that.
Well, this is bifundamental, just that we're only studying it to first order now.
Yes, but then this is effectively like vector model calculation.
Yeah. So if this theory exists for finite alpha, if we can certainly calculate any order alpha correction to this in principle.
Right.
And now, I mean, if the belief is that any M over N expansion will have finite radius of convergence, it should exist to some finite value of M over N.
Right. So maybe that is the fixed point that is most interesting.
Yeah, that's the fixed point which is perhaps most interesting, and we'll discuss that in the next slide. In fact, in next 2 slides. But as for the infrared fixed point, we don't know the value of epsilon critical when alpha is 1, but if we just guess it from what we know at large alpha and small alpha, it seems like it's less than 1. So probably that. So at least there's serious doubts whether that theory actually extends to D equals 2. But again, you can answer if you go to higher orders or something, you can try to get a better estimate for this. Okay, and these are the eigenvalues of the so the stability depends actually on alpha on epsilon for the IR fixed point. So initially there are 2 stable directions and one becomes unstable. The UE fixed point is when epsilon is non-zero, all 3 are all 3 eigenvalues are negative, so it's sort of like an ultraviolet stable fixed point. So it seems like it's like an asymptotically safe definition of the theory, if you wish. Okay, but there's one subtlety, which is that in exactly D equals 3, one of the directions becomes marginal. But before I go that, I'll just say you can also solve for the flows in the lambda 1, lambda 2 plane exactly. And these are the flows. So the UV fixed point flows to the IR fixed point, and the free fixed point also flows to the IR fixed point.
That exactly marginal guy in D equals 3 is just that sextet coupling, right? Isn't that right?
Is the sextic is the triple trace coupling?
Yeah, that 6 guy. Right. Triple trace.
There are 3 sextic couplings, but the one which is triple trace.
Okay. Yeah. Sorry.
Yeah. So which is sort of known to be marginal. Okay. So let's look at D equals 3 exactly. So if we just look at D equals 3 exactly and epsilon is 0, when you solve for the beta function for lambda 1, you get this non-zero value, 360 over pi squared. Then beta lambda 2 equals 0 implies lambda 2 is 0. And then when you look for beta lambda 3, it vanishes identically for all lambda 3. So because lambda 3 is marginal, you can't be certain of the existence of such a fixed point until we look at higher order corrections. Okay, but this is one of the class of fixed points when D equals 3. There's another non-trivial solution, D equals 3. You could have a solution where the double trace coupling is non-zero, but the triple trace coupling is 0. I mean, the single trace coupling is 0, and then lambda 3 is marginal. And the third class is where you have the single and double trace couplings 0, and lambda 3 is marginal. Okay, when you take epsilon goes to 0, actually you get a fixed value for lambda 3, but that's not reliable.
What happened to the double trace fixed point in that, you talked about these pictures as you change epsilon there, things merge.
Yeah, when epsilon is non-zero, this double trace and triple trace fixed point don't exist.
Yeah, well, yeah, the triple trace fixed point is just the free theory, right?
Well, it would be the vector model theory. Yeah.
No, I meant in the next guy. Yeah.
Well, no, but lambda 3 is marginal and undetermined.
Fine.
Okay, so these are, so in d equals 3, if you just plug in d equals 3 and turn off epsilon, you have in principle 3 classes of fixed points, all of which have a marginal direction from lambda 3. So the question is, do these fixed points exist otherwise? So to answer whether they exist, what I do is I study fixed points when n is large but m is finite, and then I take the limit m goes to infinity. Okay, and then we find one fixed point that approaches the triple trace fixed point when m goes to infinity, and we find 5, actually 3, because two of these are strong coupling, but we find a few fixed points that approach the single trace bifundamental fixed point. So although I said it has a marginal direction, if you keep m finite and then solve for the beta function and take the limit m goes to infinity, you find that there is a fixed point without any marginal directions. So it does seem to suggest that yes, this bifundamental UV fixed point exists in d equals 3. And there's no double trace fixed points found when m is finite. There's no guarantee, of course, these fixed points are the same as fixed points you get if you just went to higher order in alpha. Because here we're taking m finite and then taking m to infinity, which is a little different than doing a higher order correction in alpha.
Sorry, how about large m with ratio fixed? That kind of a calculation you cannot do?
If you keep m and n both large and the ratio fixed, then it's all fixed in order 1, then all planar diagrams contribute. So you can't include all the.
So even 1 over n expansion doesn't help because of the matrix structure, I guess, right?
Yeah, because of the matrix structure. So there's too many diagrams to solve. So
yeah, but
when n is large and m is finite, we can solve it, and it's similar to this solution we just did. Okay, so I'll then briefly discuss these fixed points and mostly focusing on d equals 3. But as I said earlier, there are several fixed points which, when m goes to infinity, approach the single trace bifundamental fixed point, UV fixed point. So we do suspect it does exist, even though the lambda 3 direction is marginal. Okay, so again, when you solve this theory, when n is finite and m is large, the exact same argument I gave you earlier applies, and the for loop beta functions are the complete beta functions, and any correction is suppressed by 1 over n, or 1 over n squared in this case. So we can determine interacting fixed points in d equals 3, as well as fixed points that are valid to all orders in the parameter epsilon hat. And here, all the 3 couplings are now on the same footing because they're all triple trace couplings. Okay, so to study it, it's convenient to write the beta functions as gradient of a potential. where you have with a metric, and when m equals 2, the 3 couplings are not independent. So, and of course, when m equals 1, the 3 couplings are also not independent. So those 2 cases have to be studied separately. Okay, and so we find for different values of m, we find actually a rich collection of UV fixed points, which sort of generalize the Pisarski's fixed point, and a few IR fixed points as well.
So this is keeping the same diagrams as you would in a vector theory, but with a few flavor indices, a few
flavor indices, and now there are 3 couplings. Yeah. There are 3 vectorial couplings,
and
all of which are triple trace. So it's just a standard vector model. If you wish, it's a generalization of Pisarski's vector model where m is now not 1, but 2 or 3 or 4.
Right. But it's the same set of diagrams, effectively.
Yeah, so from the point of view of Feynman diagrams, there's no more diagrams to be involved. Yeah, the factors, the numbers in front of each diagram are, but the beta function now is three coupled beta functions.
I understand, it's different physics, but yeah, right. Thank you.
But it's essentially the same. I mean, you could have done it in 1982. And we find generalizations of the UV fixed points and generalizations of the IR fixed points for different m. So I guess I'll go through them quickly. So for m equals 1, there are 2. Pisarski found a UV fixed point and an IR fixed point, which are very similar to what I showed you last time. And you can generalize these to arbitrary m just straightforwardly. So it's in d equals 3, it's this is more or less the same picture that I showed you earlier, that you have a UV fixed point, which here I'm calling this UV fixed point A+. And then IR fixed point here is this free theory because it's d equals 3. And okay, in fact, maybe and you can solve for stability of these 2 fixed points. And when m is greater than 1, the IR fixed point is stable only in one direction and unstable in 2 directions. So it becomes more unstable when m becomes 2. And the UV fixed points is stable in 2 directions and stable in 1. Although one of these becomes large. If we go to m equals 2, there are 2 couplings, and we can solve for the fixed points of these 2 couplings as a function of epsilon, and it gives you a sort of a complicated structure. So literally in d equals 3, there are 4 fixed points, which I call the free fixed point, this fixed point A, this fixed point C, and this fixed point B. You can now increase this parameter epsilon hat and see what happens to the fixed points, and they merge. I mean, this also there's some new fixed points sort of appear and then merge with the older fixed points. And unlike the case of m equals 1, you find 2 fixed points which survive for arbitrary large epsilon hat. So this is the picture. I mean, it's and in this plot, I mean, we arrange the fixed points according to their potential. So RG flow is only possible from this direction to this direction, and the color specifies stability. Okay, and you can look at flows from these fixed points amongst themselves exactly in the large n limit, and these are what the flows look like. So this fixed point here is like an ultraviolet stable fixed point, and it can flow to all the other fixed points. So it's sort of like a definition for the theory in the large n limit. So that's realization of asymptotic safety, sort of.
Hello?
That's the case when m equals 2. If you go to m equals 3, you get a more complicated diagram. And I guess I won't go through the details of it. Here are the fixed points when you are in as a function of n for t equals 3.
I haven't followed these. Could I?
Yeah.
In the case m equals 1, I sort of understand this Pisarski kind of picture. Let's say m equals 1 and d equals 3. Then we've got this double sort of 0 at the origin and one more guy.
Yeah.
Right. Now you turn on m, let's say m is 5. First, are there 2 fixed points or more?
There are more than 2 fixed points. There are several fixed points. Okay. So in d equals 3, there are. So let's go m equals 2. Just say.
Okay.
Okay. So your m equals 2, and now you have this parameter epsilon hat. Maybe you're mostly interested epsilon hat being 0.
Yeah. Let's say for concreteness.
Yeah. So then here for m equals 2, there are 3 interacting fixed points and the free fixed points.
I see.
Okay. And this guy has, and these fixed points in this diagram are arranged according to increasing potential. So flow is only possible from this larger u to smaller u.
Right.
Okay, so I mean, these are all 3 are UV fixed points from the point of view of the free theory, but within each other, they can flow to each other. I mean, this B plus can flow to this fixed point, which is C plus, and B plus can flow to A plus. And
the guy that's most stable, the guy at the lowest, that is completely attractive within the space of sextic couplings?
Yeah, so the most attractive guy in D equals 3 is always the free theory.
Right.
In D equals 3, literally. If you turn on epsilon, then you get an IR fixed point as well.
Right. Right. And so the free guy is always attractive, though you have to go to quadratic order to see that. Is that right?
Well, this is exact. I mean, this is quartic. I mean, this is exact when n is large.
So what I said is that the anomalous dimension around the free point, all the sextic operators have anomalous dimension 0. Right. But if you go to one higher order in,
well, they all have order 0, and you have to go to epsilon to see the fact that it's
okay.
So, yeah. Well, when you go to epsilon non-zero, then the free point is not attractive because it can flow to an infrared fixed point.
It can flow to an
infrared proportional to epsilon.
Yeah, and what is this infrared fixed point?
So even Pisarski had an infrared fixed point because that double zero bits.
The one in the middle, yes.
Yeah, the one very close to epsilon. So in m equals 2, for very small epsilon, it's literally the infrared fixed point picture isn't necessarily changed.
Okay, and that one, the one that it flows to your infrared fixed point, that one is completely stable in the space of sextic couplings.
Well, no, it had in fact one unstable direction for m equals 2.
Oh, then where does that flow to?
It flows. So this is the case in d equals 3. Here it can flow to strong coupling.
I see.
So here are the flows. So this is the flows in d equals 3. So here's a UV's the most unstable fixed point in the UV, this blue fixed point. It can flow to the green fixed point. It can flow to the red fixed point, or it can flow to the black fixed point, which is the free fixed point. And this red fixed point can flow to the black fixed point. This green fixed point, I think it's attractive in this direction, and this other direction, it flows to strong coupling. And the black fixed point, it's attractive in on this side, but it's repulsive on this side. Okay, when you turn on epsilon, you'll get another fixed point, but effectively, it's like just 2 fixed points very close to this black fixed point.
And do you suspect that the flow away from the black fixed point takes you to a mass gap?
Well, I don't know. How do you decide that? But it presumably.
Okay, thank you.
Yeah. Now, as you turn on epsilon, you actually find a fixed point. So this red line is a truly stable fixed point. So for epsilon above this critical value, this 1.2, and less epsilon tilde between this range, you have the stable fixed point. But I mean, that's not really a physical range. I mean, right. I don't know.
And just to verify for Pisarski, in the case m equals 1, the intermediate IR fixed point was truly stable, right?
Yeah, because there's only one coupling.
Right. Yeah.
So from the point of view of that one coupling, it's stable, but there's another coupling in that direction also.
Right. Thank you.
Okay, and another difference from m equals 1 is there are only two fixed points which merge at some value epsilon. Here we find some fixed points which survive for all epsilon. So hypothetically, they could go to d equals 2. At least we don't have any argument that they shouldn't.
Thank you.
And yeah, these are the flows. So you in m equals 2, you can plot these flows. For m equals 3, there are 3 couplings. So I didn't plot the flows. And if you want to see what are the fixed points in literally d equals 3 as a function of m, for m equals 3, there are these 3 interacting fixed, there are these 4 interacting fixed points and the 3 fixed points. Then, some of these fixed points sort of merge as you increase m, and for large m, you have a total of these 6 interacting fixed points when m is large.
You could compute a quantum effective potential for some field, let's say for trace phi bar phi in this problem, and then try to see what happens in the direction that the beta function takes you to, the unstable direction of the black beta function. And if that quantum effective potential develops an instability, that would tell you something, I think.
Yeah, even amongst flows between the fixed points, there's a question of spontaneous breaking of conformal in there that you could study.
Right. Thank you.
Yeah, so I mean, hypothetically, these can be studied. I just looked at what are the fixed points and their stability and their value of potential.
Right.
So here, I don't even know whether there are flows between these fixed points, but if there's a flow, it can only be from right to left.
Yeah, I was just saying that for the question of where does this in you have one fixed point which has the most stable fixed point has an unstable direction. Try to understand where that takes you. You might get some information for that from the quantum effective potential if one was interested.
Yeah. That's I can look at that. Yeah, so these are fixed points, and now you can ask, okay, how does this approach the results of the previous section? So these are those 5 fixed points and the large m behavior of those fixed points. When m is, so first we take n goes to infinity and m is finite, then we take the limit m large. So m is still finite compared to n. So we see here d plus and d minus are like strongly interacting fixed points, which we would miss from the previous analysis because I told you you could have new fixed points with strong coupling. And these 3 fixed points, b plus, e minus, and e plus, they all reduce to the UV fixed points of the previous section. Okay, so that UV fixed point, which had a marginal direction for lambda 3, splits sort of when you take finite m effects into 3 different fixed points. In d equals 3. It splits into 3 fixed points. And if you turn on epsilon, however, and take the large n limit, you find most of these fixed points merge at the value of epsilon, which is proportional to 1 over m. So they, except for this fixed point e plus and this other fixed point, which correspond to the UV and IR fixed points, and these 2 strongly coupled fixed points which interact between them. So ultimately, we find for finite epsilon, e plus literally reduces to the UV fixed point. This particular finite m fixed point, and And there's another fixed point which reduces to the IR fixed point, and they merge at a value which, as m tends to infinity, becomes equal to the value we got in the previous section. Okay, well, one moderately interesting feature about this is that there's sort of a discontinuity near epsilon equals 0 in this solution. So it sort of rapidly changes from some value at epsilon equals 0 to a different value when epsilon is not 0. So in this sense, it's sort of like the large M limit doesn't commute with the epsilon goes to 0 limit. But otherwise it nicely reduces the UV fixed point. So I guess I'll just come to the conclusion. So the question of whether or not it's possible to construct a strongly interacting conformal field theory whose large M limit is dominated by a web of inner diagrams is still sort of unanswered in D equals 3 minus epsilon, but we discovered two candidate fixed points. One was the infrared fixed point, which we study in D equals 3 minus epsilon in hopes that it would survive for D equals 2. And the other is the UV bifundamental fixed point in D equals 3. Okay, and both these fixed points, we can say something about them. So we can't conclusively demonstrate their existence or non-existence in a strong coupling limit, but perturbative calculations weren't able to rule out the existence of either fixed point. Okay, and
so sorry, did you just show that last sentence? However, perturbative. What was it? Unable.
So in the case of D equals 4 minus epsilon, just perturbation theory ruled out the fixed point at alpha equals 1. Here we can't conclusively rule out either fixed points using the perturbative calculations we've done.
Okay, and just to understand, in that case of D equals 4 minus epsilon, that happened because perturbatively your anomalous dimensions became complex, right? Do I understand?
Yeah, or the fixed point just ceased to exist.
Or it ceased to exist. Okay, and sorry, I slightly lost the thread towards the very end. Why is it that you can't do that? Because your fixed point continues to exist in the anomalous dimension?
Yeah, so we found the fixed point existed at finite alpha just in the epsilon expansion without the problem.
And the anomalous dimensions also were all real. Is that right?
Yeah, they're all real. Yeah, and they're sort of guaranteed to be real.
Yeah. Okay, I see. All right, thank you.
And then there's also this UV fixed point in D equals 3. So I think using the finite M results, you can say that at least we're certain that a UV fixed point exists, despite the fact one of the directions is marginal in the strictly M equals infinity limit. Because it exists when M is finite. What happens at larger values of alpha is still unknown. Okay, so and for the IR fixed point, of course, there is we expect it'll only survive up to some critical value of epsilon, which we don't know what it is. We can estimate it, and the estimate, suggests maybe it's less than 1. So that's the question that needs to be answered in principle. Okay, and the anomalous dimensions that depend on alpha obtain their maximum at alpha equals 1, as you would expect. Just you might have, and you could try to calculate more anomalous dimensions than just these, like higher spin anomalous dimensions, or at higher orders, and see exactly the dependence on alpha. So why these are interesting is that now we have these questions, and it doesn't seem beyond the scope of possibility that you can try to answer some of these questions using numerical bootstrap techniques or even analytic bootstrap. So that's one avenue of future research. There are other open questions. The other open questions are well, what can we do similar calculation with 6 minus epsilon dimensions for all theories with fermions? Okay, you could consider a supersymmetric theory without a gauge field, like just the n equals 1 supersymmetric generalization of the critical ON model and make that bifundamental. We expect actually that would exist in D equals 3 when M and N is 1. So maybe that has a dual description, although there's no gauge field. So, and and when one can for these finite M fixed points or for the UV fixed point, you can add a Chern-Simons gauge field and see what changes happened and whether there's, I mean, we have a rich collection of fixed points, and do they map under Bosenization duality to fixed points of a critical fermionic theory, where it's now not just, one fixed point to one, but a rather complicated set of fixed points. But the calculations seem very difficult to do in that case. So I'm not sure, because they're 1 over n, whether those are possible. Okay, those are the open questions. I have some results over 6 minus epsilon. If you want, I can share them or leave them.
Where you turn on phi cube and add flip
Yeah.
to that?
Yeah. But these are essentially the open questions for future work.
So, Shiroman, in 2 dimensions, have you not thought about this problem directly in 2 dimensions? Can one approach this anyway?
I mean, people, ask, is there a 2D CFT,
Right. I mean, the symmetry is bigger, right? So I was hoping maybe Virasoro will buy you something. Chiral nature.
Yeah, I mean, you can always ask these questions directly in T equals 2, and there's many more techniques. I mean,
because just for single scalar, like minimal models, these are related to minimal models, right? So I would imagine, I don't know.
Yeah, I mean, you can just if the theory exists, what you should be able to write down what the candidate is, I guess.
Right. In terms of gauge WZW model or something like that.
I mean, I guess I suspect the theory doesn't extend to D equals 2, for the reason that there is this critical value of epsilon.
No, but some of these things did go to, very high epsilon, right?
Yeah, well, for finite M and large N, we have theory fixed points which which could extend to T equals 2. Right. So one question is just what are these? Is there a candidate 2D CFT for these guys? And I haven't looked at that question yet. Thanks. And perhaps that can be answered actually. Okay, so let me just sketch what happens in 6 minus epsilon. So here you have a cubic coupling, so you actually need to introduce a second field with symmetric traceless indices. And then you get effectively 2 coupling constants, which are both single trace. Okay, and you can look for fixed points of the 2 function as a function of alpha. Okay, so you find so this green, these are the 2 coupling constants, and the horizontal axis is alpha. So you find, yeah.
Sorry, Shiroman. Can you just show your previous slide once more? Just okay. Yeah, just the 6-dimensional. What were the 2 couplings? Okay,
yeah. So let's look at. So here we have a cubic theory. Yeah. So you can't draw like if I want to draw a 3 guy with different colors, it's not going to be possible because what you'd color draw here. So what we do is we have a field. This field is is symmetric and traceless in ON. So it has two ON indices, and then you have another field phi, which is bifundamental. Okay, and
I see.
so we have two fields. One of them is a symmetric traceless in ON. The other one is bifundamental.
Oh.
And because you have a symmetric traceless in ON, you can have two couplings. You can just have a sigma cubed, a rho cubed coupling. So this is rho sigma, and you can have a rho phi coupling. And this actually reduces to the 5D ON model if you take sigma, if you take, in this case, n very small, then it's rho is just like the auxiliary field sigma. And it's effectively the critical ON model in 6 minus epsilon dimensions. I mean, ideally you would want this to be, you would add the trace of this guy. So, but in the limit, in the large n limit, it's almost the same.
Okay.
So this is the thing, and the point is there are no double trace or triple trace couplings, but there are two single trace couplings. So you'll have these two couplings mix with, I mean, so that's the sort of fixed points you're looking for with two single trace couplings. So
got it. Thank you.
Okay, and so we define these two TUF couplings, which I just denote as X and Y. And you get a beta function, which this is just the one loop beta function, which depends on X and Y and alpha as a parameter. And we look for what are the fixed points of this beta function as a function of alpha. Okay, and is there a critical value alpha where the fixed point doesn't exist? That's just the question. So here I'm plotting on the vertical axis. This is the value of one of the couplings, which is X squared, and this is the value of the other coupling, which is alpha times Y squared. And this green line denotes a fixed point, which is essentially the vector model fixed point, at least when alpha is small. So we find that this vector model fixed point ceases to exist at a critical value of alpha, and it merges with another fixed point. However, there's sort of this third fixed point which survives for all alpha. So although there is a critical value of alpha, which is rather small for these theories, there happen to be three fixed points, which the third fixed point exists for all alpha. And this is the value of the other coupling constant. You also get some purely imaginary fixed points, which might or might not be interesting. Okay, so, and here are the anomalous dimensions as a function of alpha as well. So, so the first two fixed points sort of merge at this critical value, whereas the third fixed point just goes on. And I mean, these graphs look very similar to like a lambda transition of like super fluidity, and so maybe if you're thinking of alpha as some sort of flux, then the system may sort of undergo a phase transition as you increase alpha beyond the critical value. So here, this is sort of the most stable fixed point when alpha is less than this critical value, and above it, it's transitions to a different fixed point. And that's basically the story in 6 minus epsilon dimensions, I mean, as of now. But we'll yeah.
Go ahead. No, so bottom line is, what is it in 6 minus epsilon? Also, you have, I don't know, you have several fixed points, but all right. Yeah.
Yeah. So here you have in 6 minus epsilon, you have a, it looks like there's a critical value of alpha, but there's actually a third fixed point which goes beyond. So
yeah. Sorry, and all anomalous dimensions are real along it, or what?
Yeah. So all anomalous dimensions are are real along these fixed points,
Yeah.
along the blue fixed point and here and here. So the question is whether this blue fixed point is strongly interacting or not, but it does exist for all alpha.
Okay. And what happens to the anomalous dimensions as you move along in alpha? They saturate
so they seem to saturate. So this is the graph of the anomalous dimension. So when alpha is large, one of the anomalous dimensions saturates to some value, and in the one loop calculation, and the other anomalous dimension sort of goes to a small zero value.
I see.
Okay, if you're looking at the other fixed points which exist up to critical value, it's sort of like at the critical value, the anomalous dimensions are maximum or very close to that.
Got it.
And as far as stability goes, this green fixed point is the stable one, and the other two are unstable. So if your system was in the most stable fixed point, then for small alpha, it will be in this green fixed point, and until it stops existing, in which case it has to go to this blue fixed point. So that's the current state in 6 minus epsilon. Dimensions. Yeah, I mean, you would like to look at higher order corrections in epsilon to see whether this, these graphs could be modified, and then there's the alpha dependence. Interesting, but of course these theories would all have this sort of like exponentially suppressed imaginary parts of the enormous dimensions, I think, because there's a cubic interaction in N.
Let's
that's different.
Let's thank Shiroman for a very nice talk. Are there more questions?
So Shiroman, just to understand what the most optimistic hope might be. Suppose we take this UV fixed point in D equals 3, and we are able to follow it by bootstrap to large to m equals n.
Right.
The most optimistic hope might be that the dimensions of all singlet un times um or on times on singlet operators becomes large except for the stress tensor. Is this right?
Yes, this is right.
And it could be that the dimensions of the non-singlets stay sort of small, but you probably don't care.
Yeah, I guess you can always, because it's D equals 3, you can just put the gauge field at 0 coupling.
This is the expectation for Chern-Simons kind of thing, right? Or even for this just a scalar model. You expect the gravity dual for that?
Well, it's true that the higher spin currents would not have a log S dependence in their spin if there's no Chern-Simons, if the lambda is 0. So whether that's a truly, so if that implies that there's no strictly dual, but as I was saying, in the most optimistic scenario, it's a strongly interacting matrix model, and everything, all the anomalous dimensions of singlet operators could diverge except the stress tensor. So it would be a theory with so presumably it has a gravitational dual, even though you didn't make the Chern-Simons coupling strong, you just kept it at infinitely weak coupling to restrict to singlet set.
Then what would lambda parameter be in the gravity dual?
Lambda would be Well, as we said, lambda would be a dilaton in axion, because if you have two Chern-Simons stage fields, you could add with equal or unequal coupling. So if you make them equal, it's a dilaton; unequal, it's an axion. Though I guess in the ON case, I'm not sure if there's an ON version of an axion. But yeah, the Chern-Simons thing means you get a dilaton at least. I mean, because that's a coupling that's marginal.
Okay.
Right.
You know.
And a stress tensor, not just the stress tensor.
Yeah. You know, I'm sorry to be so poorly informed, and all of you know this better, but Shiroman, now the higher spin currents, let's take this theory about which Shira said you have these hopes. There's no Chern-Simons coupling turned on, but you have M and N, let's say M is of order N, but even in M over N, the higher spin currents acquire masses. I mean, they're not conserved, is it?
Yeah, they're not conserved when this is, because then this sextic interaction is just a full-on single trace interaction.
Okay.
When M is equal to N. So it'll affect every. So certainly none of them are conserved. I mean,
none of them
because.
Okay, right. Yes, go ahead.
In the usual story, this corresponds to some change in boundary condition, right? I mean, I have not studied this in detail, but isn't this quartic coupling?
Well, in a vector model limit, it's a change in boundary condition, right? If you make it if it's like a single trace operator,
okay,
then it's so yeah. In the higher spin gauge state, initially it's like you have this change boundary condition. And then you increase M over N and the interactions somehow, which do depend, I guess, initially on the change boundary condition. But if M is 1 and M and N are order 1, then I don't think it's just a change boundary condition.
Okay.
I see. So then just to understand, sorry, the previous exchanges also with what Shiraz was asking. So the point is, there's no only conserved current then is the stress tensor, and if your fixed point survives up till M equals N, then there's reason to hope that it's a gravity theory, or at least one with, say, the stress tensor, maybe a few low energy operators, and all the higher spin currents gapped out in a big way. I'm just again.
Right. It's conceivable if this survives to alpha equals 1.
I see. And is this something bootstrap people can realistically hope to do? I mean, in some ways it's easier. You have no Chern-Simons couplings.
Yeah. That's the intention, is that because you have no Chern-Simons, you can look at it from bootstrap. But I'm not sure how to access this UV like fixed point from bootstrap. I mean, they can. I mean, of course, the quartic fixed point they access via bootstrap pretty reliably, and presumably even in the ON case there is this sextic fixed point in D equals 3 that it's weakly interacting when N is, well, that they should be able to determine that, see that exists.
Yeah, that's what I mean. Knowing nothing, all of you know more. I'm sorry, but since it exists at small m over n, right?
Yeah.
Then you.
Indeed.
I mean, can they set it up at weak coupling in that sense, and then just hope to follow it? Is that at all feasible?
I think that there's a scope for bootstrap, both analytic and numeric. I mean, at least if you want to go to many powers of M over N, it could be possible analytically using bootstrap. And numerically, I haven't seen people try to access the sextic fixed point numerical bootstrap, but we sort of know it exists, so maybe it can be accessed numerically with a numerical bootstrap. And I don't know. So I think both. I mean, these are questions which one can. There's a chance of doing them via bootstrap. I mean, okay. that's the motivation there. For me, I believe it might be the case, but I haven't.
Okay, thank you. Thanks, Shiroman, and thanks all.
Yeah.
Thank you very much, Shiroman. That was great.
Thanks so much for giving me this chance to speak.
Thanks.
Hey, thank you. Thanks a